Sanibonani abangani bami. Igama lami nguPaul nesibongo sami nguDevet. Ngiyajabula ukunazi.
So I was really blessed to be able to attend this magnificent school, Hilton College, a place of significant privilege. During my time here, I enjoyed excellent maths teachers, and they in fact inspired me to become a maths teacher myself. Having enjoyed such privilege, I now feel that it's time to look for ways to give back and to share that privilege with others.
So I've spent the last 25 years teaching, and I believe I've become highly effective. Let's hear from some of my students.
He was a great motivation to me.
He always believed in me and asked me to do better.
An exceptional and dedicated teacher.
Privileged to have been taught by Mr. Devet.
So dedicated and passionate about what he does.
And teaches every lesson with a passion and energy.
You should work harder and do more, just because of the example that Mr. Devet sets.
It's like we didn't work out of a textbook either, which was really nice.
I've always had a passion for mentoring new teachers and young teachers. Let's hear from some of them.
He's somebody who gives selflessly and is always looking to grow and develop others.
It was Paul who actually said to me, I need to start thinking about being an HOD.
I did not get a chance to meet him. I don't think today I'll be in a position where I am.
He has been a great colleague, mentor, and source of knowledge.
So I'd always thought that I would follow in my father's footsteps and become a headmaster. However, I've now realized that my real passion is in teaching maths and helping others teach maths. And so I've decided that's what I want to commit the rest of my working life to.
So manipulatives are models, sometimes physical, sometimes virtual or digital, which pupils can use to engage with in order to build and grow their understanding of concepts. They're tremendously powerful, and hopefully these few examples will demonstrate this. So one of the things that pupils really struggle with is the whole idea of integers, positive and negative numbers. So what we're going to do, we're going to model some sums here using yellow discs to represent positive ones and red discs to represent negative ones. So if we just start off with something very simple like positive 2, add positive 4. So there's 2 yellow ones representing the positive 2. And now we're going to add in another 4 yellow ones. 1, 2, 3, 4. And not surprisingly, we end up with positive 6. Positive 5. Take away 4 yellow ones. So positive 5 yellow ones. Then subtract or take away 4 yellow ones. 1, 2, 3, 4. Not surprisingly, leaving us with 1. Positive 2. Add in 4 negatives. 1, 2, 3, 4. And what we see now is that we get what we call 0 pairs, where a red and a yellow one actually cancel one another out, and we're left with 2 red ones, giving us negative 2. Negative 3. Add negative 2. So we bring in 3 red ones to represent the negative 3, and we add in another 2 red ones, giving a total of negative 5. Positive 5, take away negative 2. So here we've got positive 5. Now we need to take away negative 2. We don't have any negatives to take away, but what we can do is we can add some 0 pairs, because remember, a 0 pair does not change the value. So there's our positive 5, and we've got 2 0 pairs. But now we have the ability to take away our negative 2. Take away 2 red ones, leaving us with 7 as a final answer. Okay, so what we've got here is a whole lot of 1 centimeter cubes. And if we give each pupil, say, 12 1 centimeter cubes and get them to arrange them in kind of different formats, we can get them to calculate the volumes of each of their shapes. Obviously, each of them will be 12 centimeters cubed, but also the surface areas. And it's really by playing with solid shapes like this that pupils really start to understand the concepts of area and volume in a very real way. Okay, so in this little illustration, we're going to demonstrate the fact that all triangles have angles that add up to 180 degrees. So what we do is we get each pupil to kind of draw their own triangle, cut it out, and then what we're going to do is we're going to get them to tear off the corners of their triangle. and then they can always arrange their corners on a straight line. And that's a nifty demonstration that the angles of a triangle always add to 180 degrees, irrespective of what triangle they started with. So here we have a virtual manipulative showing the same thing. The angles of a triangle always add to 180 degrees. So here's another virtual manipulative to help pupils understand why the angles of a triangle always add to 180 degrees. And in fact, this diagram can be used to prove this result. So we need to be completely intentional about kind of keeping it real, about trying to help pupils understand the connections to the real world, looking for ways to kind of hook them and engage their interest. So for example, by way of an introduction to a lesson on fractions, which would you prefer, 2/3 of this pizza or 3/5 of this pizza? Would you like kind of 2 of these larger slices, or perhaps 3 of these smaller slices? And what we're going to do in this particular topic is teach you how to make that decision. So here we've got a virtual manipulative, which allows us to explore the different angles that are formed by parallel lines, and pupils can kind of engage with this and really enhance the understanding of why all these relevant angles are equal. Okay, so what we've got here, we've got a triangle with 3 different sides. The angles and the sides are kind of written, the lengths of the sides are written on them. At the moment, we've got the base over here. The height is the highest point down perpendicularly to the base. So what I'm going to do is I'm going to hook a height on there just to show us. All right, so we've got this green base and the green height which comes down to there, hanging perpendicularly. But I could turn the triangle around so that it actually has that side of 150 mils, the yellow side as a base. Then the height actually moves to being hanging down there. Right, and notice that the height actually falls. It's the perpendicular height above the base. It actually falls outside of the triangle. Likewise, I could turn the triangle so that the blue side is the base. Right, and now the height is the highest point. You can just hook on the blue height, and once again we get a height that falls outside of the triangle. Right, just to show you the actual calculations, there's a green base, a blue base, and a yellow base, and notice that, not surprisingly, we get the same answers for each. Just for interest's sake, there's also some trigonometry that we can use as an alternative method of calculating areas in grade 12, and then also Heron's formula. And unsurprisingly, we get the same answer, irrespective of the method we use. Okay, so what we've got over here, we've made a parallelogram. The opposite sides are equal in length, right? But we can see that as we kind of move it, we can see that in fact a rectangle is just a special case of a parallelogram. We can also start looking at the kind of properties, and if we look at a sort of extreme case, you can see that there's no ways the diagonals are going to be equal in length. This diagonal is going to be much longer than this diagonal. However, in the special case where we have a rectangle, I think you can see that the diagonals will be equal in length.